Welcome to the Deep Dive, your shortcut to being well-informed, fast.
Yeah.
Today, we're plunging into a world you interact with constantly, but rarely really see. The hidden universe of embedded systems.
That's right.
These are the silent workhorses powering, well, everything. The car you drive, maybe the smart thermostat in your home.
The traffic lights, the power grids keeping cities running, they're everywhere.
And here's where this story takes a pretty serious turn.
Yeah. These foundational systems, the very backbone of our modern lives, they're under increasing attack.
And not just random attacks, right?
No, not at all. We're seeing sophisticated, sometimes state-sponsored threat groups. You hear names like Mission 2025, Volt Typhoon. They're actively targeting critical sectors.
Just
like aerospace, defense, healthcare systems, telecom networks, manufacturing operations, areas absolutely integral to national and economic security.
Wow. Okay, so these aren't abstract threats. They're real targeted assaults on infrastructure that, well, touches every one of us. So our mission today is to unpack the distinct and, frankly, urgent cybersecurity challenges facing these essential embedded systems.
Mm-hmm.
We're drawing deep insights from a recent article on 3 challenges in embedded system security.
And in this deep dive, you'll get a clearer picture of what we're calling the trillion-dollar code problem.
Yeah.
We'll also look at how just, connecting devices dramatically expands the potential for attacks.
The attack surface, yeah.
Exactly. And the unique, often really tricky difficulties of securing critical legacy systems, the old stuff that's still running everything.
So why does this matter to you listening? Because understanding these vulnerabilities is key to truly appreciating the complex, often invisible effort that goes into making the devices and infrastructure you rely on every single day secure.
It's about seeing the unseen battle for digital safety.
Okay, let's get started. We've set the stage with the sheer scale of the threat. Now let's get into the nitty-gritty of why these systems are so vulnerable. Starting with what's been dubbed the trillion-dollar code problem sounds ominous. What is that, fundamentally?
It's a huge challenge, really. The core issue is that a vast amount of embedded applications, especially, older ones, are written in what we call memory-unsafe languages.
Memory unsafe.
Primarily C and C++ code. Think of it like building a house, maybe, with a blueprint that doesn't define the exact size of each room.
Okay.
So without strict boundaries, data can kind of spill over. That leads to buffer overflows, where information writes beyond its allocated space or accessing memory that's already been freed up, which we call a use after free error.
Right. And these aren't just minor glitches.
Oh, no. These are not just obscure coding mistakes. They are the most common backdoors, the main ways attackers exploit embedded systems.
That sounds like a fundamental design flaw that's been kind of baked in for decades.
It has, in many ways.
So, security experts, even government agencies like CISA, the Cybersecurity and Infrastructure Security Agency, they're pushing for a move to memory-safe languages, like Rust.
They are, yes.
Why isn't this just happening then? Seems like an obvious fix.
Well, it's not just a dilemma. It's sort of a multi-trillion-dollar catch-22.
Trillion, okay.
Yeah, I mean, if you think about the bigger picture, a complete rewrite of all this legacy code, moving it to safer languages, it's often just economically and logistically impossible, or close to it.
Like rebuilding a city's foundations while everyone's still living there.
Exactly. That's a good analogy.
Yeah.
For many companies, you're talking years of recording, exhaustive testing, recertification.
Age delays.
Massive delays. It impacts time to market, product reliability, and the sheer expense could easily run into billions. That diverts resources away from innovation, from building new things.
So it's not practical to just rip everything out and start again?
Mm-hmm.
Makes sense. What's the proposed path forward then, if a full rewrite isn't really on the table?
It's more of a hybrid approach, really. The suggestion is to selectively rewrite only the most critical components in safer languages. Apply security by design where you can make the biggest impact.
Target the highest risk areas.
Precisely. And at the same time, you apply what are called runtime protections to mitigate vulnerabilities in the existing code, the binaries.
So you protect the old code while gradually introducing safer new code.
Right. This dual approach lets companies keep innovating, keep things running, without needing that full-scale replacement immediately. It buys time and reduces the immediate risk.
Okay, so while we're grappling with that fundamental language problem, there's another dimension of vulnerability that's rapidly emerging. It feels a bit counterintuitive, but the very act of connecting these devices, making them smart, is actually making them more vulnerable, right?
It absolutely is.
That brings us to our second challenge.
Yeah.
This expanding attack surface with connectivity.
Yeah, the whole landscape has changed. The rise of connectivity in embedded devices through IoT, 5G, edge computing, cloud integrations, it's just dramatically expanded their attack surface.
So devices that used to be isolated.
Exactly. Devices that were once isolated, effectively secure by default just by being offline, are now exposed. Exposed to remote access, data exfiltration.
Stealing data out of the system.
Right, and distributed attacks too.
Yeah.
Think about IoT devices connecting everything from smart homes to industrial sensors, countless new entry points.
In 5G, edge computing.
They bring processing closer to the devices, which increases functionality, sure, but also their exposure. And cloud integrations mean devices are constantly talking to remote servers, sharing data, new avenues for interception or command and control by attackers.
You mentioned the expanding attack surface, and I remember reading this fascinating but honestly pretty disturbing story about Georgia Tech researchers. Can you tell us about that? They hijacked industrial controls with just a web browser? How?
Yeah, what makes that Georgia Tech example so chilling isn't just that they could hijack industrial controls, but how easy it was, relatively speaking. They exploited embedded web servers found in PLC's programmable logic controllers.
The brains behind factory machines, critical infrastructure.
Exactly those. By simply manipulating inputs through a standard web browser, they showed how attackers could get full control over motors, power relays, even water pumps.
Wow.
And what's particularly alarming is that they managed to remain virtually undetectable, even after the hardware was reset.
Undetectable. That's scary.
It really forces us to confront that some of our most critical systems might be vulnerable to the most, mundane-seeming attack vectors simply because they weren't originally designed for this interconnected world.
That's a powerful reminder. Complex systems, simple weaknesses.
Yeah.
So what's the underlying problem here? Why are so many devices vulnerable like this?
Well, fundamentally, many embedded systems just weren't designed with external communication in mind. Their purpose was often internal, isolated operation.
They're built for a different era.
Exactly. Retrofitting them for connected environments often leaves significant security gaps. It's like bolting a modern high-security front door onto a house with paper-thin walls.
It doesn't solve the core issue.
Right. And then there's the increased reliance on third-party software, open-source libraries, components from the supply chain.
The supply chain risk.
Yeah, all of which introduce additional, often untracked risks. If a vulnerability pops up in one shared component, it can instantly compromise countless devices that use it.
So given this huge attack surface, they have these design challenges, what's the necessary response? What do we actually do?
It really requires a proactive cybersecurity approach throughout the entire device lifecycle.
From beginning to end.
Yes. That means secure software development practices. Things like threat modeling, where you actually try to anticipate attacks and design defenses before you even write the code. And generating SMOM's software bills of materials.
Like an ingredient list for software?
Exactly like that. It's crucial for tracking vulnerabilities in your supply chain. If a flaw is found in some library everyone uses, you need to know if you're using it. It also demands continuous vulnerability assessment, scanning for weaknesses, and robust runtime threat mitigation, protecting the code while it's actually running.
So protection isn't just about the network edge anymore.
No, absolutely not. Critically, embedded systems must be protected internally too. At the firmware level, the core operating instructions, and the binary level, the actual executable code. The goal is to resist exploitation even if an attacker does get past the network defenses.
Okay, that makes sense. Build defenses in depth. So we've talked about the code itself, the C++ problem, and the expanding attack surface from connectivity. But what about the systems that have been running for, decades? The ones underpinning critical infrastructure.
The legacy systems.
Right. That brings us to our third challenge, and maybe the most entrenched one. Securing legacy systems. What makes these such a persistent headache?
They really are. These legacy systems, still active in manufacturing, transport, healthcare, they present a unique set of problems. Often, they rely on outdated hardware, outdated software stacks, built for a world before today's threats even existed.
So they don't work well with modern security tools.
Frequently, no. They lack compatibility.
Yeah.
And a huge issue is they might no longer get vendor support. No more security patches.
Leaving them wide open to known exploits.
Exactly. It's like leaving the back door not just unlocked, but wide open with a welcome mat.
So if there's such a clear risk, why are they still around? Why aren't organizations just replacing them? Seems obvious, but...
Yep. It seems obvious, but replacing them is often incredibly expensive or operationally disruptive, massively so. We're
Oh,
talking about machinery, infrastructure, stuff that's been running reliably for decades, maybe the entire life of a factory or a power plant.
right.
The cost of a full replacement or just the downtime needed to implement it can be astronomical. So organizations are often forced to try and secure systems that were never, ever designed for today's threat landscape.
It's a tough balancing act. Operational needs versus security risk.
A very complex one.
That clarifies things.
Yeah.
So, what are the practical solutions then? What can be done for these legacy systems, given those constraints?
Well, for any new development, you absolutely have to enforce cybersecurity requirements from day one. That's table stakes now.
But for the systems already out there?
For those, it means conducting regular, thorough vulnerability assessments. You have to know where the weaknesses are. And crucially, deploying runtime protections, tools that can harden the existing binaries, the running code in place.
Without changing the source code or hardware.
Exactly. That's the key benefit for legacy systems.